Hi, it's Kamgal. In this video, we're going to discuss oxidation and reduction and go over the specific reagents that can perform these reactions. First, let's differentiate the two. You might have heard that some fancy electron stuff goes down in these reactions. And that's true, but in organic chemistry, we view oxidation and reduction from a different perspective. We say that oxidation happens when we gain oxygen or lose hydrogen. And that makes sense because oxidation sounds like gaining oxygen. In contrast, reduction happens when we lose oxygen or gain hydrogen. Let's see an example of what this might look like. Here we have an alcohol and it has two carbons. Its molecular formula is C2H6O. If we wanted to oxidize it, we can turn it into an aldehyde. And its molecular formula would become C2H4O. How do we know that this was oxidized? Well, if we look at the molecular formula, we see that we went from 6 hydrogens to 4 hydrogens, and losing hydrogens is one of the ways that we perform oxidation. If we want to oxidize this aldehyde further, we can turn it into a carboxylic acid, giving us a molecular formula of C2H4O2. And if we notice the molecular formula here changed and we increased in the amount of oxygens we had, right? We gained an additional oxygen. And so that directly means that we are oxidizing this aldehyde. So we see here that the levels go from alcohol to aldehyde to carboxylic acid being the most oxidized. And when we do this, we want to make sure we keep our structure at 2 carbons, because whenever you do an oxidation-reduction reaction, the amount of carbons must stay the same. So we notice that we started off with 2 carbons, and then we went to 2 carbons in our aldehyde, and 2 carbons in our carboxylic acid. We never increased in the amount of carbons we had. We always stayed at 2 carbons. Now let's talk about some of the reagents that can perform these reactions. To get from an alcohol to an aldehyde, we use something called PCC, which stands for pyridinium chlorochromate, although I'll doubt you'll need to know that. Most professors just call it PCC. However, if we want to turn this alcohol straight into a carboxylic acid, we're going to use something called the Jones reagent, which is chromium trioxide, CrO3, diluted in hydrosulfuric acid, H2SO4. However, most professors just call it Jones for short. But I would be aware that Jones uses chromium, so you can identify it in case your professor writes it out like this. Now I want you to think critically. What do you think we should add to the aldehyde to turn it into a carboxylic acid? Should we add Jones or PCC? We would use the Jones reagent because it's much stronger. Unlike PCC, Jones can oxidize all the way to the carboxylic acid stage. PCC could never, because PCC can only take alcohols to the aldehyde or to the ketone step. And you might be wondering now about ketones because I haven't showed you that yet. And that's because in order to form a ketone, we need to use a secondary alcohol. So this over here is a primary alcohol because the alcohol branches from a carbon that only has one other carbon alkyl group. So let's draw a secondary alcohol to see why. This alcohol is secondary because it's branching off of a carbon that has 2 carbon alkyl groups. And if we oxidize this using PCC, we can draw out what the structure would look like. So remember that we need to keep the amount of carbons the same. So if we have 3 carbons here, we need to keep it at 3 carbons in our next step. So we can draw our 3 carbon skeleton, And we know that the oxygen was branching off of this middle carbon. So that's where we need to draw our carbonyl group, or C double bond O group. And so we see here that we've drawn a ketone instead of an aldehyde. And that's just because we started off with a secondary alcohol group. Now I want you to think critically and tell me what would happen if we add Jones to this ketone. Would we get a carboxylic acid? And the answer is no, a carboxylic acid would not form here, because if we wanted to keep our 3-carbon chain and draw out a carboxylic acid group over here, we would break this carbon's octet rule. Remember that the carbon cannot have more than 4 bonds, and this carbon over here has 5. Carboxylic acid here cannot form. And you might be thinking, well, can't I just draw the OH group over here and form a carboxylic acid? And the answer is no, because now you only have 2 carbons. And remember that we started off with 3, so we have to keep it at 3 carbons over here as well. So this could not form. And we would have no reaction. Now I want you to think critically and tell me what would happen if we add Jones to this secondary alcohol. What would we get? Would we get a carboxylic acid? And the answer is no, right? For the same reasons before, we would not get a carboxylic acid. However, the Jones still can perform some level of oxidation, and so it'll actually take us to this ketone step over here. So as a recap, whether you add PCC or Jones to this secondary alcohol, you are going to get this ketone, because this secondary alcohol cannot possibly form a carboxylic acid. And we saw that over here. Now, what if we have a tertiary alcohol? What would happen if we, let's say, add some PCC to this tertiary alcohol? Can we form a ketone or an aldehyde? And the answer is that we would have no reaction here as well, because there's no way we can possibly form a ketone here without compromising one of the carbons. Even if we somehow tried and added another bond, we would be breaking this carbon's octet rule. Carbon cannot have 5 bonds like it does over here, so this is a big no-no. And so even if we add Jones here, we would result with no reaction as well. And this leads us to the conclusion that tertiary alcohols cannot be oxidized. Now, if we went ahead and reversed this series of reactions, so we're going from a carboxylic acid over to an aldehyde and further to an alcohol, then we would be doing reduction reactions. And we know that because here we are losing oxygen, and that's part of reduction, and here we are gaining hydrogen, and that's also another part of reduction. But now, what reagents can perform these reactions? One of the most famous reagents that you're going to have to be familiar with is LiAlH4, lithium aluminum hydride. Yikes, that's a mouthful. But what I want you to know about LiAlH4 is a very strong reducing agent. And it can take carboxylic acids all the way to alcohols. It's so strong that it can not only reduce carboxylic acids, but it can also reduce esters, aldehydes, and ketones. So you're going to see this guy pretty often. A lot of the time, students confuse LiAlH4 with NaBH4. And NaBH4 is a less stronger reducing agent. And we see here that NaBH4 can reduce this aldehyde to an alcohol. However, we cannot use NaBH4 to reduce this carboxylic acid into anything. It would simply not work because NaBH4 is not strong enough. So let's make a list to contrast the two so we don't get confused. So we said that LiAlH4 can reduce carboxylic acids, esters, aldehydes, ketones, and acid halides. So like acid chloride or acid bromide. It can reduce those all to alcohols. Whereas NaBH4 can only reduce aldehydes, ketones, and acid chlorides. And it'll reduce those to alcohols as well. So if we think about who's stronger, we would say that LiAlH4 is stronger because it can reduce way more oxidized structures such as carboxylic acids and esters, and NaBH4 can't do that. To test your understanding, we have this ester over here. And what do you think would be the product of the reaction if we added some NaBH4 to this ester? If you said no reaction, your answer would be correct. And that's because we saw here that NaBH4 is not strong enough to reduce esters. Only LiAlH4 can. And so if we wanted to reduce this ester, we would have to use LiAlH4. So if we wanted to reduce this ester, we would have to use LiAlH4. And to draw the product of that reaction, we need to maintain the same amount of carbons. So if we have 2 carbons here, we got to make sure that our product has 2 carbons. So we would draw our 2-carbon skeleton. We can add an alcohol group onto this carbon, and so we would get a 2-carbon alcohol structure when we reduce this ester.
So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!